Hello everyone, I am Ms. Karnya Sai. Today I am here to PowerPoint presentation of CAE2. The subject name is ECA, Electronic Circuit Analysis. And the topic is Q factor and its importance in tuned amplifiers. Introduction to Q factor. The Q factor or the quality factor is a dimensionless parameter that measures the selectivity and efficiency of a resonant circuit. It quantifies how underdamped an oscillator or resonant circuit is, which affects its bandwidth and performance. Understanding the Q factor is crucial for designing effective tuned amplifiers in various applications. This is how we define it as a quality factor Q. Q is equals to 2.2 time average energy stored by lost energy per cycle of oscillation. This is the formula for finding the Q factor. Is equals to 2.2 W by PL. For the dominant mode of TE, we get this formula QTE101 is equals to K square plus C square into ABC by del of into 2B into A square AQ plus CQ into plus AC into A square plus C square. The definition of this Q factor, the quality factor is defined as the ratio of resonant frequency of circuit to its bandwidth. A high quality factor indicates a narrow bandwidth, which means the circuit can select a specific frequency more effectively. In a certain region, if the frequency is high, certain that type of frequency we have to select it. Conversely, as a lower Q factor suggests a broader bandwidth. That means if the quality factor is higher, the narrow bandwidth is happen. If the quality factor is lower, the bandwidth is high. This is inversely proportional to quality factor and the bandwidth. Q suggests a broader bandwidth allowing a circuit to respond a wider range of frequencies. This is the quality factor shown in the figure, value representing sharpness of frequency characteristics. When Q factor is large, the graph is like the curve is looks like a V shape, and the if the quality factor is small, the curve looks like U shape. The formula for quality factor, the Q factor can be expressed mathematically as Q is equals to F naught by del F, where F naught is the resonant frequency and del F is the bandwidth. The Q factor, the formula highlights the direct relationship between frequency selectivity and bandwidth in resonant circuits. Q factor is equals to Im XL by Im L is equals to IL by R. Q factor is equals to omega R by L by R. The Q factor is equals to 1 by R into L into root LC. Finally, the Q factor is equals to 1 by R into root of L by C. Importance of Q factors in tuned frequency amplifiers. The Q factor is critical in tune amplifiers as it determines how well the amplifiers can select and amplify a specific frequency. A high Q factor leads to better signal integrity and reduced noise, which is essential for clear audio and communication signals. Poor Q factor performance can result in distorted signals and reduced overall amplifier efficiency. These are the contents that we have to follow: the introduction to tuned amplifiers, Q factors, small signal tuned amplifiers, capacitance single tuned amplifiers, double tuned amplifiers, effect of cascading single tuned amplifiers, staggered tuned amplifiers, stability of tuned amplifiers, effect of high Q quality factor. High quality factor tuned amplifier provides excellent frequency selectivity and stability, making them suitable for applications like radio receivers. They can significantly enhance the gain at the resonant frequency while minimizing the gain at the other frequency. However, high Q factor can also lead to instability, making careful design considerations essential. Effects of low quality factor. In this low quality factor, tuned amplifiers have a broader broader bandwidth because allowing them to respond a wide range of frequencies. This can be beneficial in applications that require consistent performance across various frequency ranges. And however, a low Q quality factor can lead to increased signal distortion and reduced performance in selective application. This is the graph represents the when the quality factor is low. Applications of tuned amplifiers. Tuned amplifiers are widely used in communication systems, in, uh, including radio frequency, RF, and audio applications. They play a crucial role in filtering and applications in devices such as television, radios, and mobile phones. Understanding the Q factor helps engineer optimize these amplifiers for specific operational requirements. Designing for optimal Q factor. Designers must carefully select components and circuits configurations to achieve the desired Q factor for tuned amplifiers. The choice of these inductors, capacitors, and resistors significantly influences the Q factor and overall performance. Simulation and testing are essential steps in the design process to ensure the amplifiers meets its specification. These are the basic operational amplifier configurations. Challenges with the Q factor management. Balancing Q factor with other performance metrics such as a gain and stability presents a significant challenge for engineers. High quality factor designs may require more complex circuitry to mitigate potential issues like oscillators. Continuous advancement in technology and materials are helping address these challenges in modern tuned amplifiers. Conclusion and future directions. The Q factor remains a fundamental concept in the design and analysis of tuned amplifiers, impacting their performance significantly. Future innovations in materials and circuits designs are likely to improve a Q factor management in amplifiers. Understanding and optimizing the Q factor will continue to be vital for engineers in developing next generation communication system. Thank you.